In this video, we are going to evaluate the leaning tower of Pisa. Okay, so we have this tower of 1 by e, 1 by e to the power 1 by e to the power 1 by e to the power 1 by e, and so on. And we are going to evaluate and see what value this tower converges to. But first, let us see how or why I have chosen 1 by e over here. Basically, in one of my last videos, as shown in the tab, let's say card over here, I have shown that this tower of x by x to the power x to the power x to the power x to the power x, this tower converges to a certain value if and only if x is greater than equals to 1 by e and less than equals to e. So only for these values our tower converges. Now let's say root 2 lies in between these values, so root 2 to the power root 2 to the power root 2 and so on, this is equals to 2. It converges to a value. Okay, so here we have 1 by e, so this should also converge to a value. But how do we find out what value does it converge to? So let's see how do we proceed. Okay, so yeah, we have this tower 1 by e to the power 1 by e to the power 1 by e to the power 1 by e and so on. First of all, let this as y. First of all, let the value of the tower be y. And now we see that the tower is starting from 1 by e over here, or even if we just take out the first term and let the other towers be as it is, then we see that the other tower will still be y, since that's going to infinity and same as the original tower. So we get this expression. Now we can take log on both sides to get ln of y ln of 1 by e equals to ln of y. So we have taken log on both sides and the exponential goes in the front, so we have this. Now we can take y to the other side, and this is minus ln e equals to ln y times y inverse, and this ln e will be just 1, and if we take negative sign to other side, this will be ln of y inverse times y inverse. Okay, now we need to know something about Lambert function. In mathematics, for the function f of x equals to x e to the power x, we can't really find its inverse function by some normal ideas or some normal manipulations. So we just define the inverse function of this x e to the power x as a Lambert function of z, or Lambert function of x, let's say. And this is really helpful in mathematics, since we can find the series expansion for Lambert function of x. So whenever we get this function and we want to take its inverse, we just say it as Lambert function of x. And if we want to evaluate Lambert of 2 or Lambert of 3, anything like that, we can just use the series expansion for Lambert function. So basically, if you want to solve 2 equals to x e to the power x, we can just say that x equals to Lambert of 2. Yeah, so that is it. Yeah, so basically we can say that if f inverse x is Lambert function of x, then over here we can also say that Lambert inverse of x is actually x e to the power x. Yeah, if we want to solve 5 equals to x e to the power x, we know x to the power x is actually Lambert inverse of x, and then we can take Lambert to other side, Lambert of 5 equals to x, and then we can use series expansion or integral representations to find the value. So this is how we can solve such functions, and that's useful. And now before I proceed to our solution, we need to know something more about Lambert function. Okay, so from this definition, what we can do is we know that f of f inverse x is actually x. So over here, f of Lambert function of x will be x. Yeah, and now f of Lambert x is just Lambert of x e to the power Lambert of x will be x. So we will need this property of Lambert function in upcoming steps. So that's why I have done over here. And I also just like this, we also have f inverse of f of x as x, and we know that f inverse is actually Lambert for this purpose, and Lambert function of x e to the power x is also x. So this property will be helpful in the upcoming steps about Lambert function. Hope you got some ideas about Lambert function, and let's proceed. Now we know that sorry now we will try to take this in the form of Lambert function. So for that, what we can do is we have ln of y inverse times e to the power ln of y inverse. We can do this since they just cancel out. Now we know that z times e to the power z is just Lambert inverse of z. So this is just Lambert inverse of ln of y inverse. Yeah. Now I can take Lambert to other side. So ln of 1 equals to ln of y inverse. You can note that with the use of Lambert function, we already had y in two of the expressions, but now we have a Lambert in only one of the expressions. So that was how Lambert was helpful to us. And now we can just take exponentiate both sides. E to the power Lambert of 1 equals to y inverse, and then y equals to 1 by e to the power Lambert of 1. And now we use this property. We had Lambert of x e to the power Lambert of x as x. So we see that Lambert of x over x is 1 by e to the power Lambert of x. We can use this over here to further simplify our expression for y. So y is actually Lambert of 1 over 1, that is Lambert of 1. Okay, so we see that this expression which we have over here is actually Lambert of 1. But now how do we find the value for Lambert of 1? Okay, so for that we can use either series expansion for Lambert of x. We have Lambert of x as the following series: summation where n goes from 1 to infinity minus n to the power n minus 1 x to the power n by n factorial. So now if substitute x as 1 and evaluate the sum, we will get Lambert of 1 over here. Or the other way is also like this. We have an integral representation for Lambert of 1 as well. Lambert of 1 is integral from negative infinity to infinity dt over e to the power t minus t whole square plus pi square, and its inverse and minus 1. I know that this is hard for a typical person to do, but with the help of computers you can easily evaluate this and get the value. Okay, and also we will of course get real or let's say real value using this using these ideas, but we do also have other thing that the solution of x e to the power x equals to 1. The solution for this expression is we define x as omega. So we say that omega is a solution for this expression, and omega is a mathematical constant which solves this equation. So we can basically say that since this expression is Lambert inverse of omega, and omega equals to Lambert of 1. So we can say that Lambert of 1 is also a well-known mathematical constant that's known as omega, and the value for omega is actually 0.56714329 and goes on. Okay, So this is actually Lambert of 1, which can be found either from series or integral. And we have also defined the solution for this expression to be omega, which is a mathematical constant. So we can also say that Lambert of 1 is actually omega. So that's why I'm writing the solution, this Lambert of 1 to be omega over here. And yeah, this leaning tower of 1 by e is actually omega. Hope you got the explanation and some new ideas about Lambert of x, and it was helpful for you. Yeah, thanks for watching. Look forward to seeing you in the next video.